Jenifer Millard, it says here, fell in love with the night sky after gazing at the moon through an aging telescope, which I believe
with stars.
was yours. So thank you not only for introducing your daughter to astronomy, but for driving her here as well. So that's good. So Jen completed a astrophysics PhD in 2021, so last year. So a COVID PhD.
Yes, I'm a plague doctor.
It's one of those big sort of mask things on. And the title was The Stuff Between the Stars. And I did read a bit of it the other day. So
oh, you did?
Yeah.
I quite like the first chapter.
Online. Yeah.
Yeah. The first chapter is very accessible.
And I have to say, I admire you for the simplicity of the title of your PhD thesis compared to some.
What, The Stuff Between the Stars?
Yes.
Yeah.
Yes, it's very good. So hats off for your title for that. And in that, she explores the evolution of gas and dust fractions in the galaxy with time through observational data and through doing modelling.
So that's my next
and
slide.
She says it's nice to be the first person in the world to have seen things, which is great. But I think it's true to say your passion is doing outreach, really, isn't it? And doing things like this. And I think you have to be passionate enough to drive all of that way to be here. So thank you again. So she's now the managing editor of the Sky Guide app, and a writer and a host of popular awesome astronomy podcasts, the BBC Space Expert, a science presenter for BBC Wales, and a public speaker.
Yes.
Now. And if that wasn't enough, you also organise AstroCamp, which is, I guess, you.
Yeah, I do. I'm just glad I'm in.
And you were recently made honorary president of Barry Astronomical Society.
Yeah, so I'm earwigging on all your plans now.
All right. If they happen to have an underground reservoir they want to turn into a and then yeah, we've got something to talk about. So anyway, I'll stop that there. I'd just like to say, with that big long list of things you do, and we're very grateful for the time that you've managed to be able to find to come up and speak to us tonight.
Yeah, of course.
And the title of the talk is Galaxies and Infra-red Astronomy.
Yeah.
So I'll hand over to Jenny, and those three switches are the lights.
Yeah.
Thank you. Round of applause.
Yeah, I'm very excited to be here, basically because I want to have a nosy at the observatory and everything. So yeah, what you guys are doing and building, like the plans. I've seen the plans Chris has shown me, and it looks amazing. So yeah, I'm very pleased to be here. Yeah, so today we're going to sort of explore the invisible cosmos through island universes. So a lot of this is going to be the background to my PhD, and then at the very end I'm just going to talk a little bit about the sort of things that I did during my PhD as well. So I think, am I speaking loud enough? Is this volume okay for everyone? Yeah, okay, great. So this is who I am. We've already covered all of this. The only bit to mention is that I do sometimes do things which are not space. And that is, I like to cross stitch, and I'm owned by a cat. Because anyone who's got a cat knows that you don't own them, they own you. So in terms of the goals of this talk, we're going to go through the history of galaxies and infrared astronomy. We're going to whiz through the sort of different galaxy types, and then we're going to discover, hopefully, how important it is to look at the universe using different types of light. So that's what I want your main takeaway to be at the end of this. So we should probably begin right at the beginning, really, with the origin of the word galaxy. And it comes from the Greek, galaxius, which means milky. And of course, this is referring to the way that our galaxy, and of course, this milky is referring to the way that the Milky Way appears, our galaxy appears to us in the night sky, this beautiful spill of light, which, if you've ever been to a dark sky site, you will have been lucky enough to maybe witness something like this, with what I think are beautiful dark dust lanes marring this milky light. But, you know, a lot of other optical astronomers will disagree with you. And there is a wonderful bit of mythology. There's a wonderful Greek myth, which is to explain the existence of the Milky Way. And of course, it involves Zeus. Every Greek mythology involves Zeus, the naughty randy man. And one day he went down to Earth. He got a little bit amorous with a human lady, and the result was Hercules. So Hercules, being a half god, wasn't enough for Zeus. He wanted him to be a full god, so he took him up to Mount Olympus so that he could breastfeed off his wife Hera, thus imbuing him with the powers of a god. But Zeus, being Zeus, didn't really think to ask Hera if she would be okay with this. Hera was napping, and he just whacked the child onto the boob. and was like, have at it, Hercules. Hera woke up and was like, why is this strange child on my breast? Pushed the child away, and in doing so sprayed her breast milk across the sky. And this is what made the Milky Way.
I think we did have a trigger warning for
Yeah.
that.
Well, it's okay. No, it's ancient history, isn't it? It's ancient artwork, so it's fine. But in terms of actual first thinkings of galaxies, the first written observation of an object beyond our galaxy, which incidentally turned out to be another galaxy, dates all the way back to the 10th century with Al-Sufi, who was a Persian astronomer. And in his book of fixed stars, which is one of the earliest recordings of constellations, so this is a page from his book of fixed stars showing Ursa Major, he recorded the Andromeda galaxy as a small cloud. And that's how it stayed for a very, very long time. In fact, it was just over 100 years ago when we actually realized the true nature of these fuzzy clouds in the sky, which is astonishing really when you think about it. It was only 100 years ago we actually recognized that there were galaxies beyond our own, that we weren't the entire universe, that there were island universes out there as well. So how do we get from fuzzy clouds to island universes? Really nothing happens in terms of serious thinking until we get to the development of telescopes. Now, the development of telescopes, the invention of telescopes, is typically associated with Galileo Galilei, right? You know, he's the name that everyone always thinks about. I severely disagree with this. I would go with Leonard and Thomas Digges. Leonard Digges was an Oxford-educated mathematician, and he was a surveyor. So, you know, he's measuring heights of buildings, he's measuring the distance to objects, you know, but based on the ground. And he invented a surveyor's tool called the theodolite. This is an image of what a theodolite looked like around the time of Leonard Digges. Now, a theodolite is a magnifying tool. It aided him in measuring distances, it aided him in measuring sizes. And I don't know about you, but if you look at this, it kind of looks a bit like a tiny telescope, right? Yeah, I think that's fair. And his work with the theodolite and his surveying work, his interest in astronomy, was continued by his son, Thomas. Now, Leonard had a great interest in astronomy because he was actually the person who published the first English translation of the Copernican model of the universe. So we're talking 1500s at this point. And the Copernican model of the universe is when we change to a sun-centered model. So all of the planets orbiting the sun instead of the Earth being the center of the universe. That was the previous thinking. And he published the English version of the Copernican model in a book called Prognostication Everlasting. A few years later, his son Thomas Digges did an update to this book. And it's in this update that we find Thomas, but he's really the first to postulate that the universe is infinite. It's the first time we find written record of this, where he writes about stars extending to infinity. And this is completely different to the idea of fixed stars that even Copernicus talked about. He always talked about just like a shell of stars, just fixed, surrounding the edge of the universe as it was then. And so this different idea of having stars extending to infinity, some argue, is that Thomas actually took his father's instrument and instead of pointing it horizontally, he pointed it up at the night sky. So does this make Thomas the inventor of the telescope? Quite possibly. But either way, it's all right. There we go. By the way, we do know the Dutch eyeglass makers making a magnifying tool towards the end of the 1500s. And we know that Galileo Galilei, he never actually had one of these magnifying tools from the Dutch eyeglass makers. He heard a description of it and decided to make his own. So, you know, we have to give Galileo credit. You know, he just heard about the idea and thought, that sounds great, I'm going to make my own. So he did put a lot of work into making his telescope, his magnifying tool. And we know from his work, his 1610 work, but Galileo did undoubtedly resolve the Milky Band of our own galaxy into an apparently infinite array of stars. And this is the serious turning point for really thinking about the structure of galaxies, the structure of the universe, because at this point, the term galaxy and the term universe are very much interchangeable. They are one and the same, because our galaxy is the entire universe at this point. And so people have telescopes, they're starting to explore the night sky. In fact, there's so much out there to explore that in terms of thinking about the universe, we have to go all the way to the middle of the 18th century, so 1750s, until we get a real leap in thinking. And we go to English astronomer Thomas Wright. And he was the first to postulate about the shape of the Milky Way, the shape of our galaxy, the shape of the universe. And he was the first to think that, well, actually, maybe the Milky Way is not this kind of sphere, maybe it's a flat layer, which makes sense when you think about the way the Milky Way looks on the sky, right? You know, it's this definite band, but he was the first to really think about it. He was the first to realize that our sun is not in the center of this slab or out to one side. And he was the first to really start thinking that these nebulae, as they were called, these fuzzy blobs on the sky, shock horror, these nebulae, these fuzzy blobs on the night sky might be outside of the Milky Way, might be outside of our galaxy. His thinking inspired the German philosopher Immanuel Kant, and he started thinking about some of these spiral nebulae that had been found through telescopes, and maybe they are island universes in their own right. But that's as far as it went. It was just ideas talking. There was no real science or maths behind it, just concepts. Moving forward, we have Charles Messier. Charles Messier was comet hunter, inadvertently created the greatest catalogue of objects known to amateur astronomers. And, you know, he started charting comets and, you know, bright fuzzy blobs in the night sky after he was heavily influenced in his teen years by the great comet of 1744. And he was really the first to start cataloguing these fuzzy nebulae, these blobs that we see in the night sky. And he formally named them spiral nebulae, formally recorded them as such. A few decades later, we have Caroline and William Herschel. Always Caroline in there, because without her, he wouldn't have been able to do anything that he did. And they were the first to really start thinking and trying to quantify mathematically in a scientific manner the shape of our Milky Way. They wanted to do some experiments, made some reasonable assumptions with their experiments to try and figure out the shape of our galaxy, this flat plane that we've been thinking about for decades. So what they decided is they were going to assume that their telescope could resolve every single star that exists in the galaxy. So we don't worry about dust getting in the way. Every single star, if it's there to be seen, our telescopes can pick it up. Reasonable assumption. There are no stars beyond the edge of our galaxy. All stars in the night sky are contained within our galaxy, are contained within our universe. That's also fair, because we don't even know what's beyond the edge of the universe today. So that seems like a reasonable assumption. They also then assumed that stars are reasonably evenly distributed around the night sky. That one's a bit more dodgy, because we've already established that there's this Milky Band where there's definitely a lot more stars. But this was their first go. They had to begin somewhere. And so then what they did is pointed their telescope at 680 locations in the night sky, dotted all around, and literally counted the number of stars they could see in the circle of their telescope, and created a map. Here is their map of our Milky Way galaxy. It's a bit rubbish, isn't it? But what a good first effort, because it is flat. You know, it's longer in this direction than it is in this direction. This darker star that you've got in the middle here, this one is the sun. our location. It's not quite in the center. We know that to be true. Yeah, okay, it's pretty close to the center, but it's not quite in the center. So they got right. And I also find this structure quite interesting here, where they've got kind of this like long arm of star sticking out and like another long arm of star sticking out here, almost kind of giving hints at maybe this structure in our galaxy, maybe something going on, especially here as well. We've got some interesting spikes. So yes, I'm trying to big this up as much as possible. It isn't great, I understand that, but this is our first picture of what our galaxy looks like ever. The first scientific estimate of what our home galaxy, of what the shape of the universe was. So you've got to give it to them. Then the next big leap in terms of thinking about galaxies, spiral nebulae, these mysterious fuzzy blobs in the sky, comes from Yerle-Bros, William Parsons, around 1850 or so, middle of the 19th century. Because up until the 20th century, this guy had the biggest telescope in the world at 72 inches. It's called the Leviathan of Parsonstown, right? The biggest telescope. And he just did this, you know, for fun, because that's what rich people did in the 18th century, in the 19th century. Astronomy was like the cool thing to do. And his telescope was so large that he was actually able to become the first to map the detailed structure of some of these spiral nebulae, these fuzzy blobs. This is William Parsons' sketch from around 1845 of the Whirlpool Nebula, the Whirlpool Galaxy. This is a Hubble image of the Whirlpool Galaxy on the right. And I think it's absolutely remarkable, the detail that he's got correct. You know, he's got the secondary galaxy here. He's got absolutely the spiral arms in the right place. So they're really starting to look at these objects now in the middle of the 19th century and saying, actually, there's a lot of interesting things going on. Yes.
Worth adding in that his wife was a pioneer photographer and was the first to come across the idea of stacking photographic negatives to get better images.
I didn't know that.
Mary
That's
Field, her
amazing.
name was a maiden name. She was from, I think, Huddersfield or Halifax, North Yorkshire.
Yeah, that's an amazing factoid.
Yeah,
I
worth
didn't know
putting down
that.
again to add about the involvement of women in this as well.
Yeah, no,
Although
exactly.
She didn't encourage him to take astronomical photographs, but still.
I didn't know that. That's
Yeah.
amazing. I'm gonna have to dig into that more. So yeah, thank you for bringing that up. That's really cool. So as people like William Parsons are looking at these spiral nebulae, pulling out more detail, suddenly astronomers became very interested, and the quest became to understand the nature of these spiral nebulae. And on the subject of the importance of women, there is one woman who made it possible for us to understand the nature of these spiral nebulae. The field of galaxies, of extragalactic research, is what I did my PhD in, would not have begun without Henrietta Swan-Leavitt. She was an American astronomer, and she was employed as a computer. That's what women were employed as. And her job was to take photographic plates and measure the brightness of stars. And while she was working on this, you know, it was drudge work. It was just churning away, churning and churning away. She actually realized that some stars are very special. They change their brightnesses. They're known as Cepheid variable stars, one particular type of these variable stars. They have a very, very peculiar relationship in that their intrinsic brightness, so how bright they truly are, is directly related to how long they take to brighten and then dim again. That period of time can be measured. You can just stare at a Cepheid variable star and you can be like, right, okay, 1 day, 2 days, 3 days, however long it takes for it to dim to its minimum, climb to its maximum, then go back down to its minimum. Once you know that, you know how intrinsically bright these stars are. You then compare how bright these stars look on the sky, and the difference between how bright it appears, how bright it should be, gives you a distance. This distance was absolutely key to unlocking the universe, because prior to Henrietta Swan-Leavitt's discovery of this relationship between Cepheid variable stars, the only way we had of measuring distance was with parallax, and you can play around with parallax quite easily. So pick something in this room which is reasonably small, reasonably far away. And do this with me, otherwise I look like an idiot, right? Okay, so I'm gonna focus on the light switch over there. So you hold up your finger, okay, and close one eye, and you should find that your finger is over the light switch, okay? Oh, close your other eye, open the other one, right? And suddenly your finger jumps, okay? That apparent shift is because of the distance between your eyes. And we can do it with Earth. We can take a photograph of, say, the night sky in January, and 6 months later, when we've moved around the sun, we can take the same photograph, and that distance, stars will move. We can use it to work out how far away they are. Not good enough when you're trying to work out how far away these spiral nebulae are. We needed something like this. We needed the Cepheid variable star trick. Around the time of Henrietta Swan Leavitt.
Oh, come on.
I think someone's
got a gold.
Oh, okay, yeah, that would make sense. I was like, it's a cool trick. It's not that cool.
Right, sorry, guys.
Like,
Can I remind the people online again to switch their microphones off, please, so we don't get interruptions in the room.
Steve, mute big, I think you're done.
Okay, you're doing it online.
I can't do it, but I can see.
around the time Henrietta Swan Leavitt, so Harlow Shapley picked up her work, used this trick to measure the size of our Milky Way galaxy using these variable stars within our own galaxy. And he figured out that the sun was definitely not at the center of our galaxy. And as this work was evolving, two camps were kind of forming. One was the spiral nebulae were swirling clouds of gas forming stars firmly within our own galaxy. The other camp was that these spiral nebulae were actually island universes in their own right. So just like our Milky Way galaxy, completely separate entities. The two kind of leading this debate were Harlow Shapley and Heber Curtis, American astronomers. And Shapley argued that these nebulae were small, they were part of the Milky Way, the entire Milky Way was the universe. And that was because if the Andromeda Nebula, as it was known then, was going to be outside of our galaxy, it would have to be 10 million light years away, a number which seemed impossible at the time. Now, Heber Curtis, on the other hand, argued that we actually saw lots of novae in the Andromeda Nebula, new stars. So many that it was roughly the same number that we saw scattered across the rest of the night sky. That was his main argument for saying, well, actually, I think that means that the Andromeda Nebula is similar to the Milky Way. It's got all these novae. It's its own island universe. He also pointed out that there are dark dust lanes in this Andromeda Nebula, just like in our own Milky Way. Probably time to settle the debate, isn't it? The debate was settled by Edwin Hubble using Henrietta Swan Leavitt's Cepheid variable stars method to measure the distance to the Andromeda Nebula. And he measured it to be 1 million light years. Not too far out from the true number. It's a reasonable guess. No matter which camp you fell in, 1 million light years was much, much greater than any estimate of the size of the Milky Way at that point. So this was the final nail in the coffin for the Milky Way galaxy being the entire universe. Extragalactic astronomy had begun because we had discovered island universes. So what are these island universes that I've been going on and on and on about? Well, when you've got something new that you're looking at, first port of call is typically to kind of categorize it based on visual appearance, right? You know, you've got a bunch of fruit in the bowl, you're just gonna be like, right, put all the yellow ones together, I'll put all the orange ones together. Seems like a reasonable place to begin. And this is what we do. We call it morphology. It's 4 broad sort of categories when it comes to the way galaxies look. We've got spirals, we've got ellipticals, we've got lenticulars, and then we've got regular dwarfs as well. And when Edwin Hubble started looking at all of these island universes, he created a classification scheme, like we're putting the fruit in the different colours. He was putting the postage stamps of galaxies into neat little boxes, because that's what humans like to do. Now, he came up with this Hubble tuning fork diagram. So we've got all of the elliptical galaxies here, and then we've got normal spirals, and then barred spirals along this prong. In the middle, we've got something that sits in between ellipticals and spirals. They're called lenticulars. It is not an evolutionary path. It's a very key point, the Hubble tuning fork diagram. A lot of people thought that when he first created this diagram, galaxies went from elliptical down into spirals. Hubble never intended that at all. If anything, we think it goes this way, but again, hotly debated. But this is where the confusing terminology of early type galaxy and late type galaxy comes from. If you've ever heard of that, you may have. Early type galaxies refers to ellipticals because they were in the early part of the Hubble tuning fork diagram. Late type galaxies refers to spirals because they were later in the Hubble tuning fork diagram. I would like to remember it as early E elliptical. That's how I remember the difference. But I'm talking about these island universes. I actually said what they are. So what is a galaxy? Right. So galaxies are gravitationally bound collections of gas and stars, my favorite thing in the world, dust, all swirling around some kind of center of mass, often a black hole. And they're engulfed by wells of dark matter, but we're going to be ignoring dark matter for this talk because there's just not enough hours in the day if we start getting into dark matter. Now, ellipticals, they cover the most massive galaxies and also the smallest galaxies in the universe. If you're wondering what these black blobs are in this image, this is just where astronomers have masked out bright foreground stars to reveal the elliptical galaxies a bit more clearly. Now, ellipticals are full of ancient stars. That's what gives them their yellowish colour. Smaller, cooler, longer-lived stars dominate these galaxies. They're dense in the middle, they fade outwards towards the edge, and they're generally quite round, maybe a bit elongated, like a rugby ball. They're far, superior sport to football, but we'll talk about that too much. And that is because the stars contained within them have random motions. They're all going in all different directions. That's what sustains their shape. They're often called red and dead, and that is because they're reddish in colour, and dead because they lack significant amounts of gas and dust. So they're not going on to form new stars, not significant amounts anyway, hence the dead bit. We think that massive elliptical galaxies are formed from the mergers of other galaxies. These merger events are really violent, uses up all of their star-forming gas in a great big burst, leaving nothing for later generations. But we think that they have supermassive black holes hiding at their centres. Now, spirals are the pretty boys of the galaxy world, right? These are the ones that everyone likes to look at. They've got twisted arms, which is what gives them their name, the spiral. Very flat and thin, but they quite often have a central bulge. So the late great Sir Patrick Moore often referred to them as being two fried eggs slapped back to back, right? That was a spiral galaxy. But the problem with that analogy is that the relative dimensions are wrong, because spiral galaxies are extraordinarily thin. They've got the relative dimensions of a CD or a DVD. They're very thin, they're very fragile. Again, we've got a supermassive black hole at their heart, and they're very, very gas rich. About 10% of their mass is in the form of star-forming gas. So we're expecting lots of future generations of stars. They have a distinct colour dichotomy between the centre bulges, which are yellowish, and the spiral arms, which are blue. This is because we've got older, smaller, longer-lived stars dominating the centre region. And spiral arms, their light is dominated by massive, very hot, short-lived stars. That's why the disks are appearing more blue. They're full of rich dust lanes, which we'll come on to in a little bit. They can come in a barred form. So this is an example of spiral galaxy with a bar structure at the centre, or they can be non-barred, like you can sort of see here, and you can see here. You can have grand design spirals, where the spiral arms are well defined. That's what the grand is referring to. Or sometimes they're quite fluffy and hard to distinguish. So we call those flocculent. Now, lenticulars, they kind of sit in between. They have features of ellipticals. They also have features of spirals, because they might have a disc shape, as we can see with these dust lanes, but no real spiral arms going on. They're quite lacking in gas, like ellipticals, And sometimes face on, they can be confused for elliptical galaxies because they have that round, fuzzy, denser in the middle, fading out to the edges shape. Their formation is hotly debated. Are they fading spiral galaxies? But they're typically quite bright, so that doesn't really make sense. Have they somehow had their gas stripped by maybe passing close by another galaxy? Are they a result of a merger? Who knows? They're quite the mysterious beasties. And then we have irregular galaxies. Irregular is a catch-all term for small, medium galaxies. They can be gas and dust rich and star forming quite often. They are very susceptible to environmental effects, so gravitational tugs from other galaxies. We often find them interacting, so these are beautiful antenna galaxies, which were probably once two spiral galaxies that stray too close to each other. We've got these wonderful streamers of stars being thrown out from them. This is a zoom in there. Magellanic Clouds are irregular galaxies as well. This one here has got an off-center bulge, so it's just kind of a catch-all term for any galaxy which looks a little bit weird. And then finally, dwarf galaxies are all of the above, but small. You can get dwarf spirals, you can get dwarf ellipticals, you can get dwarf irregulars. They're very dim, they're very hard to find. So again, this is a population that we don't understand too much, but we often find them as satellites around larger galaxies like spirals or ellipticals. Today, Hubble's tuning fork looks quite different to when he began. We know of so much more variety. Part of that is because our telescopes have improved, they've become a lot more sophisticated, but part of it is because we've expanded the way we look at the universe. Now, morphology, the way galaxies look, is very subjective because, you know, what I think is a lenticular, you might say is an elliptical. What I think is a dwarf, you might say, nah, that's just a normal spiral. So how do you split those hairs? Well, we move on to something else. And even by eye, you can see that galaxies have different colours. But colour in astronomy has a very specific meaning. It is the difference in magnitude when calculated at two different wavelengths. That's what a colour means. And we can do this with galaxies. So we can look at them at one wavelength, look at them at another wavelength and get a colour by doing the difference. And we find when we do this and we make a plot of the colours of different galaxies, two very interesting blobs emerge. Things which are red, things which are blue, and a distinct lack in the middle, which tells us that whichever way these galaxies are moving, if they're going from blue to red or red to blue, whatever happens, it's happening quickly. But that's with the light we can see with our eyes. We do it in the infrared, and quite a different story emerges. So here in the optical, so we're looking at the bottom left picture of this plot now. We've got our two blobs, redder one and a bluer one. And we look to the bottom right in the infrared, and suddenly where this green valley is, this gap between the red and the blue, it's vanished. That's interesting, because we've suddenly got all these galaxies in the infrared filling the gap. So is this dichotomy that apparently appears in the galaxy population, this difference in the galaxy population, just a selection effect because we're looking with light we can see with our eyes? So on that, it's probably time to dive into the infrared. Now, the infrared is part of the electromagnetic spectrum beyond the red end of the rainbow. So it's longer wavelength light, less energetic events. We're all giving off lots of infrared light at the minute. We just can't see it. Some animals can sense it, but we can't. The light that we can see as part of the electromagnetic spectrum is an extraordinarily small part. So if we wrapped the entire electromagnetic spectrum around Earth, the amount that we would be able to see at the equator, so if you imagine taking a wedge and it's got this width at the equator, would be 1.4 kilometers. So it's like trying to understand planet Earth with a 1.4 kilometer wide wedge. That's it. This is why we need to look beyond the light we can see. And we begin in the infrared. Now, infrared was discovered quite accidentally. It was the first part of the electromagnetic spectrum beyond the light we can see with our eyes that was discovered by William Herschel, because, you know, looking at galaxies, finding Uranus wasn't enough. He had to do something else. So he discovered infrared light. And there was some thinking at the time that perhaps the different colours of the rainbow might refer to different temperatures. So he used a prism to split up sunlight into the different colours and put some thermometers in the different colours of the rainbow. But like any good scientist, he was like, aha, but what if there's a temperature gradient in the room? I need to factor this out. So he put thermometers either end of his rainbow. And to his surprise, he actually recorded the highest temperature past the red end. He had discovered something invisible that was heating his thermometer. He had discovered infrared light. He had discovered heat energy. Now, you can do this experiment still today. You can get everything on Amazon, basically. Just a photograph of someone splitting up the light using a prism. All you need is sun. It's usually a problem in Wales, but maybe you have better luck up here. Yeah. And you can see, hopefully, if you look at the thermometers right on the right-hand side, that the highest temperature is recorded just past the red end of the rainbow. So something maybe to try an outreach day. Now, in terms of astronomy with infrared light, started really slowly. We had to look at the moon in the 1850s. We had to look at the sun in the 1880s. But really, it wasn't taken seriously as a branch of astronomy until the 1950s and 60s for two reasons. One, we have to get above most of the atmosphere, because the water in our atmosphere is very, very adept at absorbing infrared light from space. So we need to get above as much of the atmosphere as possible. That involves building on high mountains like Mauna Kea. It involves going up in planes. It involves going up in balloons, and also eventually going into space. So we had to wait to develop that technology. Also, you need to cool down your infrared instruments. Because you're looking at heat energy, you're looking at the heat of the universe, your instruments aren't cold, all they'll detect is their own heat. So again, we needed to wait for this energy to mature as well. This just shows you some of the horrible absorption lines that we have in the infrared, just taking away all of the infrared light. Most of this is to do with water. So the first infrared space telescope happens in the 1980s with IRAS. And then today we've got several different options. So we recently had Herschel, which was looking deep into the infrared at long wavelengths. We also recently had Spitzer. Unfortunately, these two are no longer operational. We've now got the James Webb Space Telescope. We recently had Sophia, which was the telescope on a plane, which was amazing, but that's recently been decommissioned. We've got JCMT, which is on Hawaii. We've also got the UK Infrared Telescope as well, also in Hawaii. Again, tops of mountains up in space to avoid the atmosphere. So even though we're looking at heat energy, typically in the infrared, we're studying cool things, and often it involves cosmic dust, my favorite thing in the world. Now, cosmic dust, it's tiny solid grains. They're smaller than the width of human hair. They're made of things like carbon and oxygen and silicon, heavier elements like magnesium. And they pervade interstellar gas, a bit like smoke. That's what you've got to think about with cosmic dust grains. And we find them everywhere. So these are two infrared pictures of Jupiter, this one from the James Webb Space Telescope. And Jupiter has a beautiful secret dust ring, which we can't see in the optical, but in the infrared, it glows brilliantly and brightly. You can see it here as well in this wide field shot. We're all familiar with Saturn's beautiful icy rings, but Saturn is just this tiny blob in the middle. Also has a huge donut of dust, many, many times the size of the actual planet, invisible otherwise until we look in the infrared. Now, these tiny solid grains, these cosmic dust grains, are produced by dying stars, making heavier elements during their final days and also during their deaths. We can get them from small sun-like stars up to carbon and oxygen. Heavier elements we get from the explosive deaths of the most massive stars. Just to highlight this, this is Cassiopeia A supernova remnant as we see it in the optical. We can see the glowing gas and the leftover explosion of the star that dies. We look in the infrared, which we can see on the left here. Now this in the optical is this glowing white bit here. All of this is the glow from cosmic dust produced by this explosion, and then interacting with the cosmic dust that laces the gas between the stars. It's just extraordinary, isn't it? And then this is just for a bit of fun, this is Betelgeuse, the one that gave us all the trouble a few years ago. And when you look at it in the far infrared at very long wavelengths, you can see the shells of material, of atmosphere that's been slowly puffing off as it's been dying. And as these atmospheric layers puff off from the star, they move away, they cool, and heavier elements can condense into dust grains. And that's what you're seeing here as it starts interacting with the rest of the gas and dust in the interstellar medium, so the space between the stars. So low mass stars, they stop at carbon and oxygen, like I mentioned before, because they're just simply not massive enough to go on to heavier fusion processes that would give you the heavier elements. And as these stars progress from hydrogen burning into helium burning to make carbon and oxygen, their outer envelopes puff up. They, because of the complex interactions in their core, they kind of breathe almost, so they expand and then they contract, and this action puffs off their outer layers. As the enriched material moves out into space, it cools and condenses and forms cosmic dust. Now, more massive stars, they can produce heavier and heavier elements, so they can go beyond helium fusion. They can fuse carbon, they can fuse oxygen, they can make neon and magnesium and silicon, all the way down to iron. When they get to iron, you need energy to smash iron together. You don't produce energy. So then, with nothing to fight gravity, the stars collapse and then they explode outwards in a supernova. And the intense temperatures and pressures then make basically every other periodic table element that we know of. And some of these heavier elements can go into making cosmic dust. So cosmic dust grains absorb and obscure the light that we see with our eyes. So they absorb visible light and ultraviolet light, but they're not very good at it. So they can only absorb a bit of that energy, which is why then they only glow in the infrared, because they can heat up a little bit, but not a great amount, which is why then they're glowing with a lower energy deeper into the infrared. But with the infrared, we can do one of two things. We can either look directly at the emission from dust, which we did with Jupiter, with Saturn, or we can use it as a tool to peer through cosmic dust grains lacing gas clouds. So these are classic pillars of creation, part of the Eagle Nebula, M16, I think, in the Messier catalogue. And this is what it looks like to our eyes. This is a Hubble image. And these pillars are about 7 light years long. This is a James Webb Space Telescope image in the infrared of the very same object. And you can see how the dust is melting away. We can suddenly see inside these dusty pillars, we can reveal almost countless new stars. And it's given us an insight into star formation processes, which are simply hidden otherwise. All of these are newborn stars, all of them, and they're hidden in the optical. But in the infrared, we can reveal them. And so we can reveal astrophysical processes, which we couldn't see otherwise. The way this works is because of the longer wavelength of infrared light. The way I like to think about it is imagine a ball pit. Stick with me. I know it's weird, but stick with me. And the balls in the ball pit are grains of cosmic dust. Okay. Now, as an adult with long-ish legs, I know I'm not very tall, but with an adult as long-ish legs, I can march through the ball pit quite easily. So that infrared light can march through the cosmic dust grains. My legs are longer. They're nothing to me. A child, on the other hand, very short legs, visible wavelength legs, if you will, really struggles to get past these balls, gets stuck in there, can't get out, can't make it through to the other side because of the shorter legs, the shorter wavelength. That's exactly what's happening here. At other infrared wavelengths, we can see the glow from the cosmic dust itself. So this is an optical picture of the center of our galaxy, and then we're progressing to longer wavelengths. So you can see at shorter infrared wavelengths, we're making that dust mostly disappear. And then as we get to longer wavelengths where we're looking at very cold objects, then we can see the emission from the cosmic dust itself. Because cosmic dust is only about 10 to 20 degrees above absolute zero. So we're talking about minus 250 degrees Celsius. It's very, very cold indeed. There are actually some galaxies which are so full of cosmic dust, we can't see them in optical. Believe it or not, this blob is a galaxy. It's what all my galaxies look like in my PhD. I call it blobology instead of cosmology. And here we're going from shorter wavelengths down into the infrared. This galaxy is not here in the middle of this postage stamp. It's not here in the middle either. But as we get to longer wavelengths, it suddenly starts glowing brilliantly. So by looking in the infrared, we're revealing an entirely new galaxy population that we didn't know about before. My very favorite fact about cosmic dust is this: half of the starlight that has ever been emitted in the history of the universe has been absorbed by cosmic dust and re-radiated deep into the infrared. So if we don't look in the infrared, we are literally missing out on half of the universe. And the best way to illustrate this is our very famous friend, constellation of Orion. We're all familiar with this one. This is a classic optical image. We can see a little bit of some of the hydrogen gas glowing here, just a taster of it. Now, we look in the infrared, and suddenly the universe looks entirely different. The stars melt away, and we're seeing the emission from the dust that's weaving its way through gas like smoke particles. It has a hugely disproportionate effect on the way that we view the universe, because in the nearby universe, galaxies have about 10% of their mass in gas, and about 1% of that gas mass is dust. And yet, it absorbs half of the starlight of that galaxy. Now, if I haven't convinced you yet to love cosmic dust, you wouldn't be here without cosmic dust. It is a building block of rocky planets. It gets involved with stars. It also tells us about the history of past star formation in a galaxy, because that cosmic dust only exists because of previous generations. It's only there because stars exploded, because they puffed off their layers. Here we have an optical picture of the Andromeda Galaxy, our favourite friend. Here we have a deep infrared picture. And we can overlay the two. And hopefully you can see that the dark dust lanes, the annoying dark dust lanes that the optical astronomers hate, suddenly glowing brilliantly in the infrared. And this tells us the amount of dust, how prolific was this galaxy at forming stars in its past life? What sort of enrichment has happened because of previous generations of stars? All that information is locked up in this infrared emission from cosmic dust. This is one of my very favourite pictures of the universe. This is one of the early images released from the Herschel Space Telescope survey. And you can see it's full of blobs everywhere. Some of them have been highlighted, as you can see in these boxes. There is not a single star in this picture. Every blob that you see is a galaxy stretching back through most of the history of the universe. If we looked at this patch of the night sky with our eyes, we would see countless stars. But deep in the infrared, they melt away and reveal an entirely new universe.
Wow.
Yeah, it's cool, isn't it? Yeah. It's also useful, infrared, to help us study cosmological redshift. So that is the size of our universe. Now, can I get this to play? Okay, before I begin, because I've had this comment before, yes, it's a flat Earth. This is what happens when you try and represent 3D geometry in like 2D space. So we're going to pretend it's not, okay? Now, cosmological redshift is often attributed to Hubble, but he kind of pulled together the work of these guys. And cosmological redshift happens because we live in a very strange universe. We live in an expanding universe. Come on, play. There we go. We live in an expanding universe. And light is not immune to this stretching and expansion, because just as it takes time for us to walk to the shops, it takes time for light to travel through the universe to reach us. And as it's traveling through the universe to reach us, it's traveling through this expansion. So it gets stretched too as the universe is stretching. Light that was maybe emitted in the visible over time, billions of years, as it comes towards us, gets stretched. Its wavelength increases and increases until we can no longer see it, and it's deep into the infrared. So it's actually parts of the universe we can't access because their light has been so redshifted, the wavelength of light increased so much that it's now just in the infrared. So yet another reason to have a look in the infrared. This is just a different view of the same concept, just in case this picture helps instead. So we can see light emitted from the very first galaxies is at short wavelengths, the blue end of the rainbow, even into ultraviolet. As it makes its way towards us through an expanding universe, the wavelength increases, goes deep into the red, eventually beyond just where JWST is having a look for us right now. And a wonderful illustration of the benefits of looking in the infrared comes from the James Webb Space Telescope alignment image. So I'm hoping that you've seen this before, from many, many months ago.
Yeah.
And this was never meant to be an amazing science image. It was just made to focus the telescope. We wanted nice sharp spikes. But, and I recommend you do this, download this image when you go home and then crank up the brightness. And astonishing things poke out. So you can have a look at some of them. Look at that. Look at that spiral, boy. There it is. Look at the structure on this spiral galaxy. Just hiding there, just in the background of this infrared image. You can go down here. I mean, I don't know about you, but that really looks like the whirlpool. Look at that spiral arm sticking up out there. And again, not a science image. We just point at the universe in the infrared and we don't see stars. We see galaxies screaming at us from the earliest parts of the cosmos, from the earliest history of the universe. Up here, these look interesting. There's kind of all this material kind of stretching out here. Is that an indication of maybe an interaction? This guy's looking a bit warped. What's going on with this blob here? Interesting stuff. Again, not even in a science image. But the really interesting blobs in all of this are not the ones with the cool structure. Yeah, we all love a spiral galaxy. But actually, it's the blobs for the blobology. There's these tiny blobs, which will be the first galaxies, containing the very first stars, which we don't even know how they formed. Totally invisible in the visible, but glowing beautifully in the infrared. But we can't just look at the infrared, as cool as it is. We have to look at all the different wavelengths. So we look in the ultraviolet, we look in the optical, we get a picture of the stars. We've established that. We have a look at a galaxy deep in the infrared. We get that starlight that's been absorbed and then re-radiated by dust. We get a full picture of the light from this galaxy. So this is just wavelengths. So we're just looking through different filters here in the ultraviolet, the visible, moving into the infrared. And then this is just brightness up here. And what we do is take all these measurements, which we have in the black, and we fit models to them. And in those models, we encode the star formation history of galaxies. We encode the heavier elements that have been made by stars. We encode their masses, all sorts of information. And the best fitting model then tells us that information for that galaxy. we can get properties like how proficiently the galaxy is forming stars, the star formation rate. We can get information like the stellar mass of that galaxy. So before we detoured into the infrared, we were trying to find ways to understand galaxies. We did morphology, the way they look. And then we were like, but they're different colours. That's kind of interesting. And now that we've explored them in the optical and the infrared, and we've got some galaxy properties out, like the star formation rate and the stellar mass, we can now understand, look at the drivers behind this dichotomy, this difference in the galaxy population. What are the underlying drivers between having these blobs on the graph? Why do galaxies look different? Why are there ellipticals? Why are there spirals? So we take those basic galaxy properties of star formation rate, because that's the job of a galaxy, to make stars, and its stellar mass, how many stars it's currently got, and we can make a plot. So we plot the stellar mass against the star formation rate. Something quite interesting pops out. We've got a huge density of galaxies. Most galaxies sitting along a pretty narrow line. Trust me when I say this is a narrow line for astronomy, because we know nothing when it comes to space. So to have such a defined line like this, oh mama, that's great. That's very interesting. We also have a blob down here of very massive galaxies that aren't forming many stars. That makes sense, because we know about ellipticals, which are massive and they don't have much gas and they're not really forming stars anymore. We have some down here, which are low mass, not really forming stars. Well, they're small. Maybe those are the dwarfs. What's going on up here, though? A direct relation between the mass of your galaxy and how proficiently you can form stars. There is a tight correlation where most galaxies live, telling us this is what galaxies do for most of their lives. And they're all doing it in the same way, because there's not much scatter here at all. All right, that's cool, that's cool. That's the nearby universe. Does it hold as we move out into the cosmos? So we can do exactly the same, looking at galaxies, moving back in time at higher redshift. So I've got the translation for redshift into time, because redshift is not linear. It's very confusing. So that's what we've got in the bottom left-hand corner here. On this plot, we've got the same stellar mass against the star formation rate, and we're moving back in time as we move up the graph. So we've got nearby universe, and then going back down to 8.5 billion years ago, something like that. Now this is interesting. We've got the same link between stellar mass and star formation rate as we go back in time. This line staying the same as we go up to higher redshift. But there's a turnover. Weird. Kind of stops. So you get to a point with very massive galaxies, they just don't do as well as forming stars. Something is inhibiting star formation in the most massive galaxies. That's weird. Also, as we're going back in time, we're shifting up to higher star formation rates. So in the past, galaxies were much better at forming stars. Much better. They got way higher star formation rates. If we go all the way back, as far as we can go, using optical and infrared light, we actually see that galaxies were most efficient at forming stars about 10 billion years ago. So we actually live in a dying universe. The universe's heyday was 10 billion years ago. Loads of stars being made everywhere. And to understand this, we have to look at the fuel for star formation and also the product of star formation, so we can understand the past and also what might happen in the future, because why are we lacking star formation now? Traditionally, we use carbon monoxide to trace star forming gas. Can't do this at high redshift, not because we don't have the technology, because frankly, time is money, and that affects astronomy too. you can't stare at galaxies for long enough using carbon monoxide. But dust, oh yes, dust, which is interlaced with that star-forming gas, we can study that all the way back to very early stages in the history of the universe to help us understand why galaxies now are slowly dying. And this is actually the focus of a lot of research right now. This is the sort of research that I was doing. I was looking into why galaxies are dying in the modern universe, why they were so prolific in the past, by looking at their gas and dust content over cosmic time. There's lots of theories. Is it because there's a lack of gas in the universe today? That would make sense because we just used it all up 10 billion years ago. Is it something to do with the supermassive black holes that are lying at the heart of galaxies? Because were they that massive 10 billion years ago? Is it a later effect? Is it something to do with the environment? So are they having more interactions now, just destroying their gas? We don't know. That's what people are looking into now. That's what they're trying to figure out. So, in summary, extragalactic astronomy, or galaxies, is a very young branch of scientific research. It's only 100 years old. We've managed to figure out different galaxy types. We've discovered the importance of infrared astronomy when it comes to understanding galaxies. The importance of cosmic dust as a tool to unlock the history of galaxies. Galaxies today are dying, and we don't know why. We're trying to figure that out. So we're studying the fuel for stars, we're studying the product of stars in terms of dust, and there is much work going on in this area. And that's where we are 100 years later. So thank you very much.